Hi everyone, we are back and let's get into solving question number 2, anisotropic material. So much fun. So I have material that has been rotated 38 degrees counterclockwise around the 2-axis, and I found the stiffness matrix to be the one below. So I then measure some strain in the original coordinate system, stress in the original coordinate system to be this, this, and this. And so we're supposed to write out the stress strain values in the original coordinate system. What is the compliance tensor in this original coordinate system? What type of material is this? So I have... Let's go ahead and just set up our general notebook. Again, make sure you have this separate notebooks each time. So I have a stiffness matrix in this 38 degrees. So I'm going to do this C matrix. So that is after a 30 degrees counterclockwise rotation. So C matrix 38. I'm going to do inverse of C matrix 38 because that will give me my, so this is my S38. To transform it back into my original coordinate system, I'm going to have to do S naught is equal to T string 2 dot S38 dot inverse T stress 2, and then slash dot theta goes to, again, so initially I rotated it 38 degrees counterclockwise, so minus 38 slash n slash, we'll simplify, and I've got my values. So if I look at my S naught, let's do it matrix form, let's just look at it. So I see I've got a unique S11, a unique S22, a unique S33, a unique S44, a unique S55, and a unique S66. This is effectively to the minus 26, that's basically zero values. So these are pretty much as close to zero as you possibly can get. So when I look at this, I also have a unique S12, a unique S13, and a unique S23. So I have got basically an orthotropic material. So I have, my compliance tensor is as such. So I have, basically if we look at our compliance tensor schematically, let's zoom out. I have S11, oops. Let's erase that. I've got S11, I've got S12, I've got S13, 1, 2, 3, 1, 2, 3, 1, 2, 3. I've got S12, S22, S23, S13, S23, S33, 1, 2, 3, S44, 1, 1, 1, 2, 3, 4, S55, and then 0, 0, 0, 0, 0, S66. So I am working with an orthotropic material. So the strain in my original coordinate system, so let's go ahead and type this up. So my strain in the original coordinate system should be, or is, I'm going to go ahead and do, so my strain, so S, or E naught, is going to be equal to, I don't know, so this is going to be my E1. Again, this is reduced notation. Then I've got minus 0.004677, 0.007304. Then I've got, I don't know what E4 is, I don't know what E5 is, but I know what E6 is going to be 0.00152. So that's my strain. My stress, sig, is equal to 73. I don't know, so that's my sig2, sig3, minus 44, 74, and then my sig6. So we got that times 10 to the 6 because it's in megapascals. So I need to go ahead and solve for what those values are going to be. So let's go ahead and I could do solve. I could do E naught set equal to S naught dot sig and 10 to the 6. And what do you know? I've got my, actually, let's go ahead. It's 10 to 6. This will actually give me my values for what those are. Interesting. I see. It's 10 to 6. So you can see what those values are going to be there. So I've got my full stress strain tensors. Again, nothing too bad, nothing too scary about that. So I got those full stress strain values. Where my compliance tensor? We already solved that. What type of material is this? Orthotropic. That's it. So Again, this one's a pretty quick one, but again, the same process occurs. So expect in the exam, perhaps you're given a material where it is orthotropic, and you're going to have to go through multiple, here is my stress and strain values, what are my components of my compliance tensor. So this is an example of when you have the compliance tensor, it's actually quite hopefully straightforward to answer that question. All right, on to question number 3. See you in the next video. Thanks.